Welcome to the screencast for parts A and B of the fourth problem in the Computer Science 121 2013 Winter 2 Practice Final Exam. If you're watching all of these screencasts, hopefully you've already watched the one for parts C, D, and E of this problem. We skipped to those first because when I was reviewing the whole final exam, I found those easier to do. So now we're going to come back and do parts A and B. They looked like they required me to read all of this text that we have in here about number representation. In the process of doing C, D, and E, we already read this text, so I'm going to skip reading it right now. I'm going to dive right into the C++ language specification. The C++ language specification has the following to say about its integral types. There are 5 standard integer types: signed char, short int, long int, and long int. In this list, each type provides at least as much storage, so at least as many bits. Although C++ is really careful here, it's not even saying these things are represented by bits, as those preceding it in the list. There may also be implementation-defined extended signed integer types, so maybe the implementation of C++ here gives us even bigger things. The standard and extended signed integer types are collectively called signed integer types. Okay. Plain ints have the natural size suggested by the architecture of the execution environment. So whatever computer you're on, plain ints are the sort of normal size for that computer. The other signed integer types are provided to meet special needs. On my computer, by the way, it's a 64-bit computer, so presumably a plain int in C++ is going to be 64 bits long. On my previous computer, it was a 32-bit computer, so presumably the plain ints would have been 32 bits long. A long time ago, I had a 16-bit computer, presumably the plain ints would have been 16 bits long on that, and so on and so forth. Okay. Unsigned integers, declared unsigned, okay, shall obey the laws of arithmetic modulo 2 to the n, where n is the number of bits in the value representation of that particular size of integer. So they're going to have to implement what we've talked about as clock arithmetic, where we've got 0 up at the top of the clock, and when we do addition, we're going around the clock. So if we take -1 and we add 1, we get 0. But it's also the case that if we take our largest positive number here and we add 1, we're going to get our largest negative number. So that's actually specified in the spec for C++, which means it sounds like it wants 2's complement numbers, but notice it doesn't actually say they are 2's complement numbers, so as long as it behaves like 2's complement numbers, it can be anything we want. That's really different from what we read earlier in the Java language specification. It says, oh, these things are 8 bits long, and 16, and 32, and 64, and they're signed 2's complement integers, so it gives us lots of detail about everything, whereas C++ hasn't told us how big any of these things are. It's just said, well, the supposedly bigger ones are at least as big as the shorter ones. Long int may not even be any larger than long int. It's just not allowed to be shorter, that's all. So that's pretty vague. Okay. So it says the Java programming language was designed so that programs written in Java could be compiled on any type of computer and later run on any other type of computer that implements the Java virtual machine that runs Java programs. C++ was not. Discuss how these design targets affected the language specifications. So compiled here means translated from the high-level language that the program is written in into some lower-level language that's presumably closer to something the machine can run directly. So it's saying Java was designed to be compiled on, say, my machine here and run on your machine, and it doesn't matter that your machine might be a different processor. Your machine might not even be invented yet. Maybe I compile the code on my machine, and 5 years from now someone builds your machine, and I should be able to take the code that I compiled on my machine and move it over to your machine, copy it to your brand new machine, and as long as you have one of these Java virtual machines on it, you should be able to run my code. Now that kind of makes sense, actually. As C++ wasn't, it was designed to compile to particular machines. Well, the Java one says everything looks exactly like this. It doesn't matter what your computer is, an int is 32 bits long. And the C++ one says, well, depending on what computer you're using, an int can mean something different. It might be longer, it might be shorter. So that is pretty sensible. That is clear from the way the language specifications worked. So let's just write that out. Java is careful to specify details that may differ across machines, so code will work regardless of what the machine actually does internally. So for example, Java's 32-bit ints on my machine, they're probably going to be stored as 64-bit ints because my machine likes to work with 64-bit chunks. So 32 bits of that 64-bit chunk is just going to be wasted when I use a Java int. Whereas if I compile a C++ program for my computer, it's going to use up all 64 bits. So that seems like a waste, but on the other hand, what it means is if someone wrote code in Java that relied on those things being 32 bits long, and then they tried to move it over to my 64-bit computer and run it on my 64-bit computer, it's not going to fail just because my computer uses 64-bit integers. Right? Otherwise, it could fail. It could expect something to be true because numbers are 32 bits long, and since my numbers are 64 bits long, it gets messed up and it does the wrong thing, maybe in a really surprising way. So that's kind of a good thing. It's also kind of a bad thing because, I've got a 64-bit machine. Maybe you're listening to this on a 128-bit machine, a 256-bit machine, some huge chunk of memory that you use as your basic unit in your computer. And if you're stuck with Java, then you're still using 32-bit ints, which is a little disappointing. You're not really getting the most out of your machine. So that's sort of a good thing in Java. It means we can move between machines, but it's kind of a bad thing too, because it means Java is going to get out of date in the long run, assuming that bit widths keep getting bigger and bigger. But presumably there's lots of other things in the spec that are inflexible in the same way, and so Java's probably going to be out of date eventually. But, new machines will probably figure out ways to run Java much faster anyway. Okay. So that's the Java side. What about the C++ side? Well, C++ directly mentions the machine. The architecture of the machine. So it works hard to take advantage of the specific machine. Or at least, that's not in the specification directly, but the fact that the specification doesn't limit your compiler to this one generic Java virtual machine means that it can take advantage of your specific machine, and a really good compiler will probably be written that way. So that takes care of part A. By the way, that's a big, hard question. It is not the sort of question in this course that I would imagine asking on a final exam, but it does touch on a lot of ideas that are important to us. I mean, when we read that specification, we saw, 16-bit 2's complement signed binary integers. We should know what that means. But this is a really sort of deep language specification machine architecture issue. Maybe you're going to go on in our course sequence and take Computer Science 213 and 313, and you'll have a better idea of why these choices were made. Maybe you'll take Computer Science 311 and 411, which are on the programming language side, and you'll have a better idea of why these choices were made. Okay. Some Java and C++ programs test to see if int values in the program are negative by checking whether the 32nd bit from the right is 1. Based on the specifications for each language, is this guaranteed to be correct? Why or why not? Okay, well, the 32nd bit from the right is 1. Let's not think about that. Let's think about how we test to see whether a signed binary number is negative. And what we look at, if this is our signed binary number, we look at the leftmost bit, right? If that leftmost bit is 0, then the number is either 0 or it's positive. On the other hand, if that leftmost bit is 1, then the number is negative. So if this is bit 32 from the right here, and then this would be bit 1 and bit 2 and bit 30, bit 31, then we're doing the same thing. We're checking if the leftmost bit is a 1. So why did it say the 32nd bit from the right instead of the leftmost bit? Well, let's see if the 32nd bit from the right really is the leftmost bit. And we already said in Java, an int is 32 bits long, and it is a 2's complement signed binary number. So in Java, this really is the sign bit. And that is guaranteed. But in C++, ints may be some other length. Ints may be shorter or longer. Longer is more likely these days than 32 bits. So no guarantee that this is right. And in fact, really subtly, it doesn't even say that these are signed binary numbers in C++. So even if you knew it was 32 bits long, it's not necessarily the right thing to check the leftmost bit to see whether it is negative or non-negative. It probably is. Probably almost every computer with a C++ compiler uses signed binary numbers. But there's no guarantee in C++, where there is a guarantee in Java. Okay, and that solves these two problems.